I'm Amin. I'm an assistant professor at Harvard University. My expertise is in programming languages, and I also do AI to do systems that are intelligent web instructions, so I like to do formal verification.
Louder.
Louder? Okay. And so for these lectures, I want to do something a little on the side of what you've been looking at in this programming language summer school. So not so much on the type theory, but more on the metaprogramming, having programs that manipulate programs, some things that you can do and do very well in type theory as well, but looking at the foundations of that in like old school Lisp meta-interpreters to reflective systems, to proof by reflection, like in modern system and things like this. So we'll start with a lecture like this, and then move on to multi-stage programming, which is more type-driven in the second lecture. And then we'll look at relational programming, which I like to think of as a possible future of programming where you program with constraints and relations rather than functions. So the way I think of metaprogramming is writing programs that manipulate programs, and I think of it very broadly. As, for example, interpreters have programs as inputs, compilers have programs as inputs and outputs, you might have synthesizers, transformers, analyzers, even discovery systems in like the old school style work of Eurisco, a discovery engine that learns about its own heuristics as it's making discoveries of concepts, of heuristics, and developing them. So I think of metaprogramming.
Question. Sorry, is it okay to make the text a little bit bigger?
Oh, the text here?
Yes. Thank you.
Better? Okay. Yeah. So then the things we're looking at today are are mostly like interpreters and variations on that. And I want to say why I like metaprogramming first. So first, I think of it as something foundational, like even at the very heart of a universal computing machine, there's this idea that a program becomes data that is interpreted and manipulated. And then it's useful, so for example, building tools by building languages, building specific languages. And I like to think of ways of taking a language that already exists and adding features to it to make it a good host for metaprogramming language, and for building specific languages. And then it's kind of principled in the sense that we'll see in lecture 2, a way to mechanically turn an interpreter into a compiler, so getting the benefits of the simplicity of an interpreter, but the sort of speed that you would get by removing overhead when you do a program transformation of a compiler. And I do think it's fun, and I show a lot of code and try to make this slide even clearer. And so for the lectures here, I'll present interpreters and reflection in lecture 1. In lecture 2, I'll do look at SMT, thinking of it as a backend. So like languages that compile to SMT satisfiability modular theory solvers and the multi-stage programming as well, and thinking of them as in both cases interpreting symbolic data in one stage and getting to code in another stage. And finally, relational programming. So in terms of interpreters and reflection, we'll look at meta-circular interpreters in Scheme and Prolog. And we'll look at reflective powers of interpreters. So how do we go from something meta-circular to something that is a tower where every time you go up a level, you go from an object level to a meta level, you have some form of verification of program into data, and then when you go from the meta level back to the object level, you go from, you do a reflection from data into program. And then I'll see how this plays out in the proof setting. So looking at an old system called FALL from the 70s by in the 70s, and then see how it plays out in Amin today, where things have gotten much simpler by basically, oops, logic is old. Okay, so the system Amin has gotten much simpler, where computation is integrated in the type theory computational models. so, and then I guess I can talk about what I'll do for the next lecture. But one thing that will emerge is that languages can basically act as interfaces. So for example, SMT as a backend is an example of this. When you have a language, you can innovate above and below the language. And in this lecture, we'll see how if you have reflection, it has a bad reputation for good reason in some sense, because it allows to modify the semantics of the language as it's running, and that creates a lot of uncertainty, loses a lot of possibilities for optimization. But it also is kind of interesting in the way it allows for flexibility in inspecting computation. And so for today, the themes that I want to make important is basically thinking about representations. So higher order versus first order representation for environments, for closures, for things like this. Thinking about continuation, passing style, and trampolining, meta-circularity, towers, reflection, proof by reflection, and if we get to a discovery system. So let's dive right in our system, so maybe I can make this one bigger too. So we want to dive right into writing an interpreter that maybe for now we'll define some environment just as a placeholder. And we will say that we have an interpreter that takes an expression and environment and does something with it. So one example of what we might want to do is, for example, we might want to have this quoted expression 2 times 3, and 2 times 3 in the empty environment, and that should give us 6. So let's try to get to the point. So we do conditional. If we have a number for the expression, we just return it. So this is the condition, and this is the result. And then if we have, let's do a tagged operation. So let's do tagged times expression, and I'll define tag to be something that takes a tag, and make sure that we have a list where the first thing is the power of the tag. So we can say if pair E and equal car of E is the tag. So for example, now we can do tag times expression to 3, and we get 2 to 3. So that works. So if we did tag times expression plus we would get false. So now that we have these type things, well, what we want to do is kind of like in similarity to the notational semantics. We want to evaluate the sub-expressions and then put them together. So we would have plus of the evaluation of the catter of the expression, which gives you the first, the second element in this expression, and you have the catter of this expression. Okay, so now if we evaluate this, we get 6, and that's what we want. So now let's add features to our language. So let's add lambdas and an expression. Let's actually use the environment. So first we have to decide on our representation for the environment. And we really have, at least 2 choices. One is to represent the environment as data, and the other is to represent it as a function. In our case here, the only thing that an environment does is you want to look up a variable and get its value in the environment, and you could represent it as a function and say by default it's a function that basically just returns an error, let's just say. So we get one like this. So we get an error for the empty environment, and let's say we wanted to construct an environment which had x1. We could do this by having a function that says if x, y is x, then we return 1, as we do the empty. So this is how we can build up environments. It's really functional programming. And so we can do that. And now let's add a case for symbols. So if we have a symbol, then we just look it up in the environment. Okay, so now we can have in the environment 2x, we can have, if we take the environment x1, we have 2, so that works. So now we're going to add closures, and we're also going to use this trick of doing a higher order representation of closures. I will show later how to do first order representations. But for a higher order representation, we can kind of say that if we have an expression like lambda x times x1 times x3, and apply it to 2, that should also return, in the empty environment, that should also return, that should also return 6. And so we can add the case for closure, and we will have to add the introduction rule and the evaluation rule. So for closures, we can add a lambda case. And we can do, so we're going to represent it as a function, so it's going to be, here we're just going to do functions of one argument. So let's say we get the value as an argument for this function, and then let me just make some helper to make this easier to deal with. So I want to say that the name of the parameter is x, and it's the car, it's basically, here we have a list, so this is the getter, and then we get the car. And then here we can get the body, which is yeah, so this is kind of nicer in the typed language to play with these things, but anyway, so here we get something like this, and now we have this lambda a, which is when we'll get later the argument, we can basically evaluate the body in an extended environment. So this is where we can use our trick here for this that we did for lambda y. So we can say lambda y if x, y is x, then we return a, otherwise we return m of y. And that's basically, that just kind of, that's it. We've defined lambda in terms of lambda. Let's see that it actually works. And to do that, I have to add the application case as well. So here I have the application case, which is going to be basically, we're going to assume that we have a pair, and we're just going to apply the car of the x to the schedule.
Nada.
Yes?
Oh,
Yeah.
sorry, what do the adder and meta functions do?
Yeah, thanks. So this is a convention in list proa. So if you have a list of things, or even like with nesting, so if you do car, you get the first element of the list. You always put things between C and R. And if you can kind of do footer to get the rest of the list, so you get the rest of the list like that. And if you do catter, you get the first element of the rest of the list, so you get the 2AB. And you can keep doing this for a little bit. There is a limit in terms of but you can always nest them other ones. So that's an important question. So it's just a way of doing list manipulation. It's very low level. It's almost it's kind of really treating all the data that comes in as these nested list expressions. Yes?
Are you going to share this code?
Yeah, so there are some versions of this code available on here, on this website, and I can share it with them. I mean, it's available now on this website. So it's metaprogramming under learning. Yeah.
So in the code, I mean, I'm not very familiar with lists, but what exactly is equal in the equal function? How does equality actually work?
Equality, yeah. So this is purely equality of symbols. We're only comparing symbols. So EQ is just pointer equality, but there is also equal for like more deep equality. You can do equality for lists and things like that. But here we're only putting symbols in our environment as variables, so we can do just pointer equality. Yes?
Two questions. First, you wrote catter with two Ds.
Yeah, so this is because I have a lambda expression like this. So I want to take the body of this expression. So this is one D, and then if I put another D, it gets me to the rest of the rest.
And what does body do?
So body is the expression that represents, it's a symbolic expression, so this is really representing a list with the symbol times and the number 2 and the number 3 is symbolic. And now we're going to, whenever we get an actual argument, we're going to evaluate this body as an expression. Yeah.
I'm seeing a possible connection here between something called normalization by evaluation. Would you help connect that?
Yeah, so normalization by evaluation is a form of evaluation, except it makes sure everything is in normal form. And it kind of does a little bit of, so we will get to this when we talk about staging. We have a bit of a normalization by evaluation going on. It's like when you evaluate, and the result of evaluation is not just a value, but it might contain code. You don't want to have an arbitrary form for this code. You want to make sure it's normalized. So, for example, you might want to avoid having so for example, if you had lambda, like something like lambda x2 going to 3, well, this is kind of like something you can simplify completely at compile time to get to the value of 2, for example. So depending on how your normalizer work, that will be the kind of thing it does. And in staging, one thing that is important as well is when you have closures, you want to kind of be able to compare closures to make sure you haven't reached the same point again. And one way to do this is to normalize them. So I would say you can think of it as normalization by evaluation as a form of normalization where you have code as well. And you're kind of going from expression to expression as opposed to expression to value, but you're simplifying the expression.
I guess to that point, just to clarify my understanding, right before where your cursor is on the left, the eval body, lambda y, etc., is basically saying we're making a lambda with a bound, and we're making a body that is possibly not, if I'm trying to read it, but possibly not going to have other lambdas in it. Like we're trying to evaluate the body of it.
Yeah, so the body might have other lambdas, yes.
Yeah.
We're recursively going to be taking care of that. And I want to get to the point where I can show a bigger example. So this is the point where I want to get at. I want to get for this phase of the lecture to this test case, which is basically having all these nested things. You basically have the y combinator here and the factorial function, and without having, and just with that, without having special recursive definition in your language, just with lambdas, this should work in our system already. Mm-hmm.
Is the else part of the conditional or part of the test last condition?
Yeah, that's a good question. So else is the last case of a conditional if nothing else applies. I mean, here we kind of are using it as if we had a list, so we have to be careful to cover all the other cases, but it's kind of the last case of the conditional. Yeah.
I was gonna just, maybe you're parsing it with the if on the line above it, but
Yeah.
it's implicit.
Yeah, so this is that. Yeah. So these are all the common cases. So we have a case for number, a case for symbol, if we have a multiplication, if we have a lambda, and now we have this thing, and we still need to finish it up here with this. And this should work for, let me see if I can. So this should work for this example now, if we didn't make a mistake, and it's working. So let's just do the thing of adding whatever is required to get this test case to work. So it's kind of hard to see it with that. We have this. So we're doing factorial of 6 and the NTM. And I think we need to add a 0 question mark and if. So let me just also add, this is not strictly necessary for this example, but let's just say Boolean numbers are also self-evaluating. Then I'm going to add tagged. So these are fairly mechanical, and in a better system we would put them in a global environment or something. But here we would have this. Okay, and then we have to add if. So if is also interesting, the way it's defined in terms of itself. We kind of all have the same shape now. We can have if expression, and then we can have if. So we have the condition, and then depending on the value of the condition, we do one or the other. Sorry. Okay, I'm not giving a good reputation to this manipulation. So let's see if this works. I don't know if I forgot. We also need 0. So 0 is similar to this. So I don't know if this will work. Sometimes, okay, it works. So we did it. Yes?
I was going to ask about the encoding of if in a strictly evaluated language like this. Would we, in a different example, would we have to make a func in order to handle like short circuiting or?
Yeah, so what happens here is that I'm defining, so this is a good observation. So there's a difference between times and if in the way I've defined it. Times is something that could be handled if I had more argument with the regular application of a procedure to arguments. Evaluate the arguments and then evaluate the and then like apply the procedure. But if is a special form, which requires special handling because we're only evaluating the then and next branch if we need to. So you write that, you couldn't write if as a function, you would have to write it as a special form given this thing, and if you wanted to write it as a function, you could use stumps. Any other questions? Okay, so what have we achieved? So we achieved a small interpreter for a language that can do things like this, so recursive functions with factorials. And we can actually scale this up to a language that is truly metacircular. It doesn't have to be as complicated as what I'm showing you now, but it's just an example where I made a few different decisions. So the different decisions is now our environment is first order, it's an association list, well, a list of frames. So for example, that would be a frame, and that would be an environment having this and having two. So this is, so that would be the way we represent environment completely as a first order thing. And so then lookup is actually traversing this to do something. Yes?
Why is it why is it so nested?
Yeah. So it doesn't have to be super nested, but it's kind of convenient when you have lambda, because each lambda will introduce a new frame, and you can kind of see this frame like as popping in and popping out, as opposed to like, yeah, so it's just one operation to create a frame. So it doesn't have to be nested. It's like the nesting, it represents the nesting of this course.
So for example, like one lambda is allowed now to introduce two variables.
Exactly.
And
And then we also have, we also have a global frame where we have all the global variables. So now times is not defined especially anymore. It's just said in the global variable, it is represented by the multiplication of the underlying scheme system. And then what that means is that in the case for application, you can either have closures or primitive procedures, and you can have the both. And now closures are just this, this tag list of like having a closure, capturing the environment of the closure, capturing the parameter list, and capturing the body. And it's a little bit more sophisticated because the body can have multiple statements because there are side effects and things like this. But this is what it took to scale this to an example that can interpret itself. So basically, this whole program, I can load it here, and then I can get a REPL. So now I have a REPL with that is interpreting my thing, and I can do 2 times 3, and that works. I can load other things, so I can load some examples, and that also works. I can load the program itself, and that also works. That means I can create a new REPL here and keep going. And actually, you do notice something. So if I do it a few times, let me do it again. So you can see that the CPU time increases. Let me do it one more time. Maybe I did it too many times, but now if you do the examples, it's actually, yeah, this one is pretty slow. So there is like an interpreter overhead, and I think I did it, yeah, okay, so it's still but I think we can do it. Okay, so this is what we've got so far. We have a meta-circular interpreter that is in direct style, so we're not explicitly thinking about computation, but we're just like pending these computations and so far. So one thing we can do is kind of try to get a handle on the computation, verify the computation, make it something you can actually call and things like this. So let me accept this report. But before we move on, any questions about what we've seen so far? Is there anything that needs some clarification? Or is the gist understood? Yeah?
So a quoted number is just a number, but a quoted set of characters is a symbol.
Yeah, so quoted, so I guess it's, technically we haven't, in this interpreter we add quote as a special form. So let me see where it is. We have quote. So quote is the same as just writing quote A. This is the same as writing A, so I can write quote ABC, and this returns ABC. So quote is a very simple special form that basically a quote number in the REPL, you're actually just returning the number. But when you're evaluating a number, the number evaluates to itself. Yes?
What do you mean when you said that the interpreter is meta-circular?
So I really mean that, like in the demo that I was doing, I was loading the code of the interpreter with itself. So it doesn't mean that it spells out everything. So for example, here we have this global environment with these primitives. So we're defining times in terms of the primitive times. We're not saying what is the definition of times, but we're using it in a meta-circular way. That means it's always wired correctly for us. But it's meta-circular in that you're writing, it's really a simple definition of writing in your definition language is a language that you can interpret with your, is an object, is also your definition language is a subset of your object language. Yeah.
What happens if you quote the quoted thing? Like, will it give you a
Yeah.
single quote?
Yeah, exactly. So, I mean, I guess same thing, but it's just a shortcut. Yeah, so it really doesn't do any language. It doesn't need to know anything about the language, just returning the argument. Okay, so I wanted to show some like thinking about computation. And for this, I'm just going to, let's go back to our live setup. And I wanted to think about, like, let's just take the factorial function. And this definition that doesn't deal with numbers, but so if we trace that definition, let's do 5.6. We see that kind of the stack grows and comes back down. And that's because when we're doing this recursive call to factorial, we have this pending operation of times n. And we can try to write an iterative version that doesn't grow the stack. So for example, so the way to do it is you can take an accumulator and do, if it's 0, return the accumulator. Otherwise, you do factorial of n minus 1. And you do the operation here. And you pass it around. So actually looking for this. Okay. So now if I trace that iter, that's nice. So I have to pass it an initial thing.